right. All right, before we continue, I will just quickly give a disclaimer that whatever we discuss are your personal views based on your experiences. We are not representing any organization in any way. So my very first question would be on the sketching pattern. You are the co-inventor of the count minute sketch. So in an event-driven agent architecture, could we use sketching as a form of compressed long-term memory? Uh, I mean, this would allow an agent to remember the frequency of events across millions of streams without actually storing the raw data.
That's right, yeah. So I mean, people have found ways to use sketching and sketch-like ideas in a number of different applications. They started out for sort of massive database and networking applications. But yeah, it would be pretty natural to incorporate them into agents who, as you
Mhm.
say, want to use them as a form of compression. So the advantage of sketches compared to other data structures is it's fairly simple to implement, and it's very sort of structured in the way that it stores data. So, unlike maybe a more complex data structure where you have to handle like insertions and deletions, move things around, free memory, allocate memory, the sketch just sort of sits there and it's a fixed transformation of the input data. That works very well for some applications. It may or may not be a good fit for others. I guess I haven't seen people very explicitly using sketches in those sort of agent memory storage yet, but it may be just that I haven't been exposed to those use cases.
Got it. Yeah. And what about it's a different question on federated pre-processing. So,
Yes.
like in your recent Fed PS paper, you address the pre-processing stage of federated learning.
Hmm. Hmm.
Why is it so much harder to aggregate statistics across a distributed network
Yeah.
than it is to aggregate model weights? Like, does this solve the data quality problem for agents before they even start training?
Yeah, so that's a good introduction to quite a broad topic. So you kind of identify the key issue here, which is, there's a lot of interest in using this model of federated computation as a way of training learning systems, right? And most of the work in that area has focused on this sort of key step of how do you actually tune, optimize the model weights. And of course, that's the most obvious, and it's often the most um, costly component of the training process. But it's not the only piece. So what I'm interested in is understanding, if you're going to work in this model of federated data where you have distributed agents, distributed data, how do you do the entire machine learning pipeline, right? Not just sort of the core training step in the middle, but the pre-processing, the data preparation stage, and maybe the post-processing, evaluation, testing, leading up to deployment and even post-deployment. So if you think about that sort of training step, the big win in federated learning was to make this observation that although training, when done centralized, can be quite mathematically complex, you can simplify it slightly and essentially just say, okay, every agent optimize their parameters locally and then combine them, average them. Right? And that works pretty well for the training step. So when we were looking at pre-processing,
Hmm.
we started with exactly that question. Why can't we just compute these these sort of parameters that describe the shape of the data, or that that sort of help you normalize or fine tune it? Why can't you just compute them locally and average them? And the answer is it doesn't work so well, right? In the training step, it turns out that this averaging gets you there, and you can iterate it, and you can repeat, and you tend to converge. But for this pre-processing step, averaging, each agent, each entity sees maybe a very different data distribution. And so averaging tends to sort of, you overfit locally and then you average and you don't get actually a good description, just get a noisy result. So we looked at slightly different ways of combining that information, um, based on defining the appropriate statistics that were more possible to then combine in this sort of aggregation model.
Got it. Makes sense. Uh, on some niche questions that I had
Mhm,
on
mhm.
the Gem Plus private
Oh
synthetic
yes,
data.
yeah, yeah, yeah.
So your latest work on Gem Plus uses generator networks to create scalable synthetic data. So
Hmm.
if we can create state-of-the-art private data, does that mean the model collapse risk is actually a data quality problem that Gem Plus can solve?
I think yeah, all of these are useful useful tools. I mean, one of the sort of again one of the broader points here is, you know, generative AI is very powerful, and if you want to use generative AI to say, make me a picture of a kitten on a skateboard, it can do that for you,
Mhm.
and it can do it in different styles, and it will produce something that looks fine for that description. Um, So what we've been interested in that work that led up to Gem Plus was synthetic data. And I guess the main point I want to make is just that synthetic data, you can view it as a kind of generative AI, but it has a different set of constraints, right? The key thing is you want your synthetic data to match the real data that you're training from very well. But again, you have this sort of privacy concern. You can't just copy the real data. You've got to create new examples, new individuals in the synthetic data who are realistic, much more realistic than maybe a image generation would be, but which have the right characteristics. And so with Gem Plus, we were kind of pushing that direction and saying, in addition, this needs to be something which is scalable. This needs to be something which um, actually works well on realistic data sets that have many rows, many columns. Um, and so what we found is the state of the art in synthetic data up to now works pretty well up to a moderate number of columns, like 10, 20 columns. But real data often has hundreds of columns, and then they're hitting some kind of performance um, issue. So Gem Plus was designed to try and take the best of the existing approaches to synthetic data generation, but also make it performant, make it scalable. Um,
Mhm.
so the issue we were dealing with wasn't model collapse directly, but it was those sort of related questions about actually making this work, making this usable, make it something that practitioners could plug into their workflows.
Got it. Speaking of practitioners, on the meta lens, like
Hmm.
having been a research scientist at Facebook, you have seen privacy at the scale of billions. So,
That's right.
what
Yeah.
is the biggest scalability trap that engineers fall into when they try to implement differential privacy in a real-time streaming environment?
Yeah. Okay, yeah, that's an interesting question. I think there's a few different balls. Um, one the most basic issue is just being realistic about what you can achieve in
Mhm.
terms of the usefulness of the resulting information. Because even if you have tens of millions, hundreds of millions, billions of participants, um, if the task that you're doing depends critically on one or very small number of individuals to define, behavior in a certain sub-region, like, you have all these parameters, but maybe some parameters in your model depend critically on a few outliers. Then when firstly, that's not robust to begin with, but when you bring in privacy techniques like differential privacy, it can sort of distort a lot because the random noise that gets added for privacy just outweighs the signal that you're getting from very few individuals. Um, so the first thing to watch for is to think about what is the task that you're doing, and is it robust to the fact that even if you have a very large population to start with,
Mhm.
are you able to sort of accurately fit that model even when there is noise? Um, so the first point is just about making sure that you think not about what's the right model to use, what's the right training, what's the right overall system, but factor in the fact that there will be privacy added to that.
Mhm.
Um, then the second point is more to do with scalability and performance. That I think the main thing that engineers need to sort of understand is more just sort of certain calculations. When you go from saying, "Oh, I've got all this data," you need
Mhm.
to say, okay, how much data do I have? What rate is it coming in at? What one of the things we discovered that was sort of almost surprising is at Meta we were gathering data from, yeah, let's say up to about 1 billion Android devices, and that seemed like a lot. We're like, okay, that's going to be a lot of data.
Yeah.
But the way that the system was designed, it was very frugal in the way that it collected data. It would basically ask the device to check in, say, once or twice a day, um, and report like a few key statistics on, device performance, network measurements, and so on. And when you average that out, what sounds like a huge amount, 1 billion devices a day, um, comes out to be like a few thousand reports per second, because there's a lot of seconds in a day. And so
Yeah.
actually, because we could pace things and we could spread them out, it wasn't such a big monitoring load as it first seemed. So, sometimes big data can get smaller, but equally, if we were saying, okay, actually, we do need to measure some very like sensitive thing and we need updates, from each device many times a second, that would have swamped it, and we would have had to move to a more distributed measurement environment that, load balanced across a much larger set of hosts.
Got it. Yeah. My next question would be on the knowledge gaps. I mean, it might
Mhm,
be too
mhm,
soon to ask you this, but I want to understand what are your initial thoughts. Like you have been an ACM fellow for years.
mhm,
What
mhm.
is the number one algorithmic trick from the world of streaming data that AI engineers are missing today as they build the real-time agents?
Interesting. So from the streaming world, I'm not sure there's like one trick, but I think what I've seen among sort of software engineers is that there's good awareness of some key techniques like Bloom filters as a way of capturing large data that's describing a set of values and representing it very compactly. But there's the whole bunch of other tools that have been developed over the years, like ways of counting the number of distinct elements, that ways of tracking which are the peaks in a signal that are perhaps
Mhm.
less well known. Um, so I think my effort in that direction was, I've given like tutorials, presentations, and I wrote a book quite a few years ago now that tried to capture that from a sort of algorithms and data structure perspective.
Mhm.
Um, but maybe the gap that subsequently needs filling is to then sort of that presentation is a little bit abstract. It just says, here's a data structure that works in a certain way and has these inputs, has these outputs, it answers these queries. So I think the gap is then to sort of fill in more about, okay, where in today's sort of AI ecosystem do these tools fit? How are they useful to engineers who are building that next generation of agents? Um, it could be that maybe some of these things are no longer necessary because what we used to do, sort of handcrafting data structures, can now just be learnt. But I think within that, there's some useful patterns and paradigms that can be fit in the sort of idea of certain kinds of random projection or hashing based aggregation of data um, can be used as a sort of a bottom layer within various neural network models to help sort of pre-filter and aggregate data that then gets, perfect. Excellent. Now looking forward to seeing that.
All right, Graham. Thank you so much for your time. I'll make sure that I keep you posted about the outline of mathematics learning book as well.
Sounds great. All right. Cool.
Thank you, Graham.
Very
You
good to
have
talk with
a
you
lovely day ahead.
and you. Yeah.
Bye.
Bye for now. Bye.